So I'm going to start at 6, but you know, it's 5, well, sorry, 6 p.m. Central Daylight Time. It's 5:58 right now. That means we've got 2 minutes for you guys to ask me LabVIEW questions in the chat before I get started. Any questions? Here, I got a question. Who is attending this presentation right now at the most inconvenient time? Like I said, it's 6 p.m. in beautiful Austin, Texas right now, but anybody here like really late at night or really early in the morning? 4:30 a.m. Oh my gosh. I didn't even know there was a 4:30 a.m. Oh man. Well, I'm gonna try to get you your money's worth, VJ. All right. Stan's been here since the beginning. I must admit, I may have possibly slept through about the first hour of this whole thing, but I've been going strong since 8 a.m. Central Daylight Time. The question in the chat is it possible to make Application Builder run on multiple cores? Not currently, no. That's why I always tell people if you want your builds faster, get a machine that has the highest number next to the gigahertz word whenever speccing out the machine, because multiple cores doesn't matter. Only the speed of one core can improve your build time. All right, that was our one question. It is right at 6 p.m. Central Daylight Time. I'm going to get started because I have a lot of content. Thank you everyone for coming to my presentation. This is a presentation I've been giving for 6 years now, but I added some new content. There's about 25% new content in this presentation over what you may have seen before. So buckle up. But probably the most important thing in the entire presentation is going to be here on the first slide, and that is going to be a description of how to pronounce my last name, because I have attended the presentations in this summit so far, and multiple presenters, some of whom have known me for almost 2 decades, are pronouncing my last name wrong, which is just the worst. I mean, they've heard me say my name a million times, and they're still saying it wrong. It's Nattinger with a hard G. Here, I'll even give you guys a mnemonic. For those of you that are Americans, you probably know Tony the Tiger, the mascot for Frosted Flakes. He says, Frosted Flakes, they're great. Just remember that, and you'll remember how to pronounce my last name, Nattinger. All right, that's if you take nothing else away from this presentation, at least take away from this presentation how to properly pronounce my last name. All right, now that we got that out of the way, let's go ahead and get into the slides. So I give a lot of LabVIEW presentations. If you're here and you haven't seen me present and you don't know much about who I am, my career at NI has been a long one. I've been at NI for over 25 years, and I spent most of that time in LabVIEW R&D. That's not where I am currently. But throughout the course of my career, I have given a lot of LabVIEW presentations, and they are all available, the ones that I've done myself, on dnet.org. So I put a link in the chat. You can go there and download the slides for my presentations. You can watch video recordings of them. Hopefully this recording will be available relatively soon because, again, I've added some new content. And if you're looking for the landing page for this specific presentation, it is at bit.ly/dneterrors. So another thing before I get started, I would like to extend special thanks to Stephen Loftus-Mercer. Probably a lot of you guys have heard of Stephen, a longtime member of LabVIEW R&D. He helped me a lot working on the content for this presentation, so I just want to give him a shout out. A lot of this presentation was done in collaboration between the two of us. All right, so the crux of this presentation is that we are going to talk about how I do not like the term error handling. We all use that term, and unfortunately it's overloaded, because when you say error handling, you probably mean one of 5 different possible aspects of error handling in LabVIEW. You might be referring to error generation, which is when your LabVIEW code creates an error value on an error cluster. You might be referring to error propagation, which is when an error value is flowing through the various wires and nodes on your block diagram. You might be referring to error response, or error display, or error logging. Look at all these different aspects of error handling. Well, in today's presentation, I'm going to be focusing on error generation and error propagation, but I kind of feel like I should at least spend a few minutes covering response, display, and logging, just to sort of give you an idea of all of the different aspects of error handling, even if we're only going to focus on a couple of them in this presentation. So error response. This is what you do in your LabVIEW code when an error has occurred, when there is an error cluster that has an error value on, going through an error cluster wire. And you look at that value so that you can respond in a certain way. Maybe you want to ignore the error. Maybe you want to clear the error. Maybe you've got some code wrapped in a for loop where the error is running the condition so that you can run the code again if an error occurs. Maybe you want to take that -1 billion and something Visa error that's super cryptic and turn that into a, hey, plug in your serial cable error that's easier to understand. So maybe you're translating an error. Many more possible ways to respond to an error. The reason I'm not going to talk about this is because there is a single PDF that is a poster, although when you print it out, it's more like the shape and size of a placemat. So like maybe you can put it on your dinner table. But you can download the PDF, and it basically covers all the different ways to respond to errors. This is a resource that my colleague Stephen Loftus-Mercer put together, and he put this thing together a really long time ago. It's still valuable. The information in it is still 100% correct. The problem is, since he did it so long ago, there are some things in error generation and propagation and response in LabVIEW that are different. As an example, the clear errors VI did not have a number of error to clear input on it when this slide was made. And so you're going to, or I'm sorry, when this PDF was made. So you're going to see places in the code that you might think, why is he, unbundling and wiring and bundling a 0 when he could have just used clear errors with a number wired in? It's because we didn't have it back when this poster was made. So anyway, that's error response. What about error display? So error display is when you're basically at the end of the line. Your LabVIEW code is executed. You're at the very end of the data flow. And what are you going to do with your error? Well, you're probably going to display it in some way. Maybe you're going to display it in an error indicator. Maybe you're going to display it in a string. But a lot of the times you display it with the simple error handler or general error handler VI. I tend to use simple error handler VI 100% of the time because I can't think of any time I have used any of those other inputs to general error handler. So simple error handler is just easy to work with. Now, one interesting thing is that simple error handler VI has an input called type of dialog. And if you wire no dialog into that, then the VI will not pop up a dialog, but it will output a string that tells you the message that it would have popped up in a dialog. So if you've got your own mechanism for error display, you can still use simple error handler, just tell it no dialog and tell it to give you back the string. If this looks familiar, it might be because this is what DQMH does in its API testers. So this is all scripted code. You never have to write this code. But as you can see, when an error reported broadcast is received, we use the simple error handler VI with the no dialog input. And what that ends up doing is that ends up adding a string to your status string on your front panel to give you the error message that otherwise would have popped up in an error dialog if you had used regular simple error handler. The question in the chat is, does the message that comes back include the B tags for bolding? I think it does, but I don't remember offhand. It should be pretty easy to try out. All right, and then the last aspect of error handling that I'm just giving a quick overview on is error logging. So this is the idea of you've got your LabVIEW application, you want to log the errors to some sort of file for later analysis. Error logging is a big topic. This topic occupied an entire CLA summit. That's how big it is. And if you just go into Google and type in LabVIEW error logging framework, all these hits come up of different frameworks and solutions for error logging. So I'm not going to cover that in the presentation today, other than to give you a couple of ideas to keep in mind when logging errors. You always want to log all the errors, even the ones that your code has responded to, probably the ones that your code has translated. You want the error log to include the originals. And then you also want your error log to periodically give you some indication that it's actually running. And so even if there are no errors, maybe some sort of heartbeat that's in there to let you know that. Otherwise, what if your error logger crashed and you look at your error log and you say, hey, there's no errors, but really there were errors that your logger didn't catch. So those are my couple of quick pieces of advice for error logging. So let's go ahead and talk really quick about warnings. So warnings are error cluster values that have a non-zero code, but they have a status of false. Don't use warnings in your APIs. Errors are really, they're best handled or best dealt with as a binary. You either have an error or you don't have an error. When you include this middle ground, like maybe you have an error, like what do you do with that? Like when Visa read tells you a warning that all of the characters that you got back was equal to the size of the buffer that you were trying to read. Wait, is that bad? Is that good? I'm not sure. And so that's why I don't like warnings. They're ambiguous. So just don't use them. But my recommendation is, even if you personally don't use warnings in the APIs that you write, you should probably make sure that your code is warning aware. So that error cluster wire coming into the left side of that case structure, it might have a warning on it, but in the no error frame of the case structure, that warning would then be lost. And so you would not find out about that warning. Now, I observed this exact wiring pattern in some code that I was reviewing recently, like maybe 2 months ago. And that was code that was being written by a very well-known member of the LabVIEW community, who is one of the original authors of one of the most popular frameworks in the LabVIEW community. And I pointed out to him, hey, look, you're going to lose warnings here. And he said, good, I want to lose warnings there. I don't want any warnings making their way through my framework. And I said, whoa, you hate warnings more than I do. So some people are militantly anti-warning and they actively write code that looks like this picture. I don't go that far. I would prefer to preserve the warnings if at all possible. All right, you guys, let's get into the first of the two main sections of this presentation, which is error generation. So if you say error handling, you might be referring to error generation, which is the creation of an error value on an error cluster at the point that something goes wrong in your LabVIEW code. There are two ways that an error can be generated on a LabVIEW block diagram. The first way is pretty obvious. A built-in node that outputs an error cluster value. If you try to open a file and you give it a bad path, you're going to get file not found from the open create replace file function. If you try to enqueue an element and your queue reference is invalid, you will get an invalid queue reference error out of the enqueue function. Those sorts of things. Pretty simple errors that are output by property nodes, built-in primitives, functions, stuff like that. The second way to generate an error in LabVIEW is that you, the LabVIEW programmer, write G code that creates an error cluster value. So in the very simple screenshot we have here, we are taking a numeric value that's coming out of a call library function. We are taking that integer, and inside of error cluster from error code, we are turning that into an error cluster value that we are then wiring out. So a little bit more details about error cluster from error code. You can see here I've got a zoomed in screenshot of the VI. The only required input is that you wire the error code. You've also got an optional input to give more information with a string with an error message. You've got a Boolean for showing the call chain. That defaults to false, which in my opinion was a mistake when this VI was written. It should have defaulted to true. Here we are. So I was wire a true constant to that input. You may be wondering what this input is that I have intentionally cut off from the screenshot. That is the is warning input. Well, what did I just say before? You shouldn't be using warnings, so you should never wire that input because you should never be generating warnings. So always wire in the error in from previous code. That way, upstream errors are preserved. Always show the call chain. And in my opinion, you should always wire as much information as possible to that error message string, just to help for debugging whenever you're debugging errors that were generated with this VI. Please don't build the error cluster yourself. Do not write the code that looks like this on this picture. Maybe if you're on RT because you don't want jitter. Maybe if you're on FPGA because I don't think the string even does anything. But in general, don't build the error cluster yourself. Always use error cluster from error code. I have actually had to debug an application before where the error source string was telling me the name of a VI, but that VI was not the place that the error was being generated because somebody had written code exactly like what you see in the slide here, where they had put in the VI name as a string constant to the source, saved a copy of the VI, and then didn't bother to go rename that string constant. So don't do that. Just use error cluster from error code. It's always going to generate the proper error source string whenever you're wanting to generate an error. Now let's talk about the error ring for a moment. I first gave this presentation at NI Week 2018. You can find that recording on YouTube. And in that recording, you will see a big old cheerleader for the error ring, and that was me. I believe my exact quote in the presentation was, quote, "The error ring is fantastic. I love this feature. That is what I said almost 6 years ago. While I no longer recommend using the error ring. See, here's some of that new content I was talking about in this presentation. Uh, there's a long story as to why I don't recommend using the error ring. You can hear that whole long story in my ludicrous ways to fix broken LabVIEW code presentation, which I've included a link for in the chat. But to summarize it very quickly, error rings are built on top of a technology called X nodes, and I don't trust X nodes. Maybe I will trust them someday, but I do not trust them now, and so I do not use the error ring. I use error cluster from error code for all of my error generation. The question in the chat is, an inlined VI is not reflected in the call chain. Is there any way around that? Not to my knowledge. I mean, I think you basically would have to turn the VI into not inline, because that's the whole point of inlining, is the LabVIEW execution system does not see that VI layer. Somebody correct me if I'm wrong on that. All right, so yeah, no more error ring, sticking with error cluster from error code. So I sometimes have encountered LabVIEW programmers who ask, why do we even need error codes in the first place? And there's a couple of sort of arguments that they make. First is, why not just make everything error one? That's the easiest thing to do. Then just shove some useful information into the source string when you use error cluster from error code, and we'll just use that to debug. I have to admit, I have tried to make this argument myself in the past. And I no longer make this argument for a few reasons. Number one, it can really help when you are familiar with the error code ranges that certain APIs that you use utilize. If you get an error that comes back that starts with 1000, it's probably some sort of VI server error, like, a VI is broken and you try to run it with VI server, run VI, that sort of thing. When you see that number, you can instantly sort of key in on, okay, I've got a pretty good idea of which API might be generating this error. If everything's error one, it takes some extra work to get to that point. And another big one is end users of your application. You're probably providing information to people, testers, operators, and sometimes what you'll hear back is, yeah, I clicked on this button and I got error 1234. And you ask more questions, and literally all they know is, I just error 1234. I don't know. So if everything was error one, that's worthless. If they tell you, oh, I saw error one when I did that. So that's another reason why error codes are helpful. Again, they help you as the developer. Another argument, well, just, who cares about the error code? Just always include the call chain, then you can always track down where the error happened. Well, call chain isn't always readily available. I suggest using error cluster from error code, but sometimes, shoot, a couple minutes ago, VJ asked in the chat, what about inline VIs? Well, if there are VIs in the hierarchy that don't show up in the call chain, that could be misleading as well. And I just want to drive this point home that sometimes your end users only know, I saw error 1234 pop up. This is a big one. I see this a lot. You've got your operator, hopefully you've got a decent error logging scheme so that you can go back and review what, led to the point of the error code. But it's a big time shortcut for you as the developer if somebody can just give you an error code and say, yeah, error 1234, and then you're like, all right, well, I know where I need to go look for that. All right, so the error code numbers that you use, right? Error 7, file not found, error 1003, VI not executable. The error code ranges that LabVIEW uses and LabVIEW toolkits and modules use and NI drivers use. NI actually has a database within the company of basically all of the error code ranges that various NI products use for their errors. Well, there are a group of error code ranges that NI has reserved as saying, NI is never going to use any of the error codes in these ranges in our products. So these are basically for the LabVIEW community and anybody developing a LabVIEW API outside of NI to use for their error code ranges. So you're going to want to grab those. I see people grab the 5000s all the time. That's one of the most common ones, obviously. But as you can see here, there's quite a few other error code ranges that you can utilize for your APIs as well. Now, you could create these things called error code text files. If you have never heard of an error code text file, go into LabVIEW, go to Tools, Advanced, Edit Error Codes, and click the Help button on that dialog, and you'll learn some more about what error code text files are. It's a text file that you can distribute with your code, and it defines errors that might be used in your code so that when simple error handler or whatever is receiving that error code, it can include more information. If you are localizing your errors. So you're distributing an application that's going to be seen in multiple languages, and you want your error codes to, I'm sorry, your error descriptions to also be appearing in multiple languages. Error code text files are actually a pretty good way to sort of, take a text file and be able to have multiple copies of that are multiple languages and use those. But if you're not localizing, if you're okay with your error text being in English or whatever language you're using to develop, there is an easier way to deal with generating error values in your LabVIEW code. And I call it the Fabiola way because Fabiola de la Cueva, who was the chief architect of DQMH, when she and I were working together probably almost 10 years ago, she introduced me to this technique, and I have found it to be very effective and very easy. And if Tim's here, very simple to be able to define the error codes that are being used by my application. All right, you guys want to know what the Fabiola way is? All right, let's go. Step one, create a sub-VI wrapper for each custom error that you're defining in your application or in your API. That's what I've done here with the screenshot. You also want to give it a -- error file name suffix, and you want to give it an error glyph. So the purpose of this VI that we see on the screen is to create an error cluster value where the error code is 5001, and the message tells me that I have specified an invalid actuator ID. So that's the purpose of this VI. Now that I have this VI, in my API, in this case, it's an API that's defining a servo motor instrument driver, I'm going to call that VI whenever I need to generate that error value. So in the VI that you see there on the right, I'm assigning an actuator ID, but the first thing I'm doing is I'm checking the numeric value to see if it's within a certain range. And if it's not, I'm generating the error, okay? This is an example of an error sub-VI. Now, next step is have a folder of these error VIs in your project. So, or in my case, it's this servo motor driver. So in the servo motor driver, I've got a virtual folder where I've defined all of the possible errors that my code might generate. Now, another thing that I often like to do is I will sometimes have a spreadsheet where I keep track of the error code numbers that I have used. It's optional. You don't have to do that. Sometimes it just makes it easy for me. If I come back to this API like months later and I need a quick reference of, wait, what was the last number that I used? I can go look at the spreadsheet, but you don't necessarily have to do that, especially with something I'm going to mention in the next slide. The question in the chat is this error sub-VI inlined? It could be. I honestly don't know. It's probably not that big a deal. In general, I'm not looking too much at optimizing the error case. I'm typically looking at optimizing the no error case. The question is, merge error, do we need to set as retain all error? You do not. I'm going to talk about retain all errors in a minute. All right, so what are some benefits of the Fabiola way? First of all, there's no extra steps when you're building your EXEs and PPLs. If you're using error code text files, you've got this extra file that you need to configure in App Builder as the error codes file for your EXE or whatever. You don't have to do that with this because these are all static VIs that are just, in your code. Another benefit is that in your project or in your library, there's a one-stop shop for all G-based errors, and that's that errors subfolder that I talked about. Another benefit, if I need to drop an error sub-VI, I can very quickly type in -- error in QuickDrop and get a list of my error sub-VIs, and then just pick the one out of the list that I need. But the primary benefit, oh, sorry, one more benefit. And this is a bullet I added to the slide pretty late, which is why I forgot to put it there. It's my understanding that a future release of Antidoc is going to be able to parse your project for -- error VIs and include auto documentation of their contents in the Antidoc documentation. So then you don't even need that optional spreadsheet anymore because that's just going to be part of your project documentation. But a primary benefit of the Fabiola way of managing error generation. By the way, I didn't ask her permission to call this the Fabiola way, so hopefully she still likes it. But the primary benefit is debugging. When you have a an application or a library that's running and you encounter an error. You can right click, and you know which error it is because again, you're only ever calling your error sub VI in places where you want to generate that error. You're never using an error cluster constant. You're never using a naked error cluster from error code VI with a constant wired to it. You're using these sub VI wrappers to generate your errors. Whenever your code generates an error, find callers immediately takes you to the places in your code that could have generated this error. It drastically reduces your debugging time. And if you decide to go install my experimental project find tool that I've published on ni.com, then not only do you get the normal project find functionality, but you also get an open button in that dialog where you can multi-select the VIs and open them all at the same time. Now, normally when you double click on something in the project find dialog, it closes the project find dialog and takes you to that individual thing that you clicked. There's no multi-select option. I've published an experimental improvement to Project Find to allow you to multi-select in the list and open the VIs from there. It majorly speeds things up when you want to open multiple things from Project Find at the same time, especially in the exact use case I'm describing in the slide, when we want to go look at all the places in our code where we could have generated a particular error. Now, another shout out is that the Fabiola way of error generation is a prime example of designing for debug. I love this presentation by Norm. In this presentation, Norm talks about how important it is to make sure that when you're designing and developing your LabVIEW code, the idea of, in the future, debugging that LabVIEW code inspires the decisions you make while writing that LabVIEW code. That's exactly why I like the Fabiola way of error generation. As I'm creating those error wrapper VIs, I'm thinking, I'm obviously, using the LabVIEW editor, but I'm also thinking, man, this is going to make things way easier to debug if, eventually I have to go, explore the code. The question in the chat is finding callers necessary if you have the call chain set to true? If you have access to the call chain, you're right, you can just go straight to the VI. As I mentioned before, a lot of the times you don't have access to the call chain. So if you know it was this error that happened and that's all I know, at least that gives you a head start of where to go in your code because you know the only places where that error could be generated. All right. Second part of the presentation, error propagation. So previously I talked about error generation, your LabVIEW code creating an error cluster value. Now we're going to talk about error propagation, which is the movement of that error cluster value through your LabVIEW code. There are a lot of aspects to error propagation. For one thing, you can take an error wire and you can fork it and have it go to parallel code paths. So now you've got parallel code paths that are propagating an error. You could also take those parallel code paths and then merge the errors from them into a single place. Now we're only propagating one error. You could also wrap some code in a case structure and have the error be the selector for the case structure so that you're saying, if an error comes into this, I want the code to go through a different path. Lots of aspects to error propagation and lots of tools to facilitate error propagation. Like I mentioned, a case structure that has an error case and a no error case. Merging errors, a shift register to propagate an error from one iteration of a loop to the next. So lots of aspects, lots of tools, but one overarching rule for error propagation. And that rule is that you should never break the error chain. And when I first gave this presentation at NI Week 2018, the marketing team tried to edit my slide and take off those 2 ones at the end of the title, and I put them back. And then somebody today said, hey, there's a mistake in your slides online. You've got extra 1s after the exclamation mark. You should take those out. And I guess I'm just old because I remember the days of the internet when people would yell at each other online, unlike today. But back then, people would yell at each other online, and what they would do is they would put on their caps lock and they would start typing things on all caps. And then, the exclamation mark is on the 1 button, but the caps lock doesn't do that. So you hold the shift button down and you bang on the 1 button to put a bunch of exclamation marks when you're yelling at somebody. And sometimes you would take your hand off the shift button while you're still banging on the 1 key and throw a couple of ones on the end of all those exclamation marks when you really wanted to yell at somebody on the internet. So this is me really yelling at you guys right now, which is to never break the error chain. And the thing is that the reason I'm so passionate about this, some might even say religious about this, is because I don't know if you guys knew this, but sub-VIs and primitives in LabVIEW, they're actually really religious. You guys, did y'all know this? They have faith in a higher power. Sub-VIs have faith that the programmer, which is you're that higher power, is going to carefully take an error that they generate and shepherd that error to its final resting place. Maybe simple error handler, maybe an error indicator. Whatever it is, those sub-VIs are handing that error to you, the higher power, and asking you to shepherd it to its final resting place. All it takes is one place in a VI hierarchy that breaks that error chain to cause any node's upstream error generation to be lost forever. Or at the end of your hours-long debugging session to find the place where the error chain is broken. I have taken part in those debugging sessions, which is why there's all those exclamation marks and ones at the top. Question in the chat. I remember you saying to not do LabVIEW on Rails. That's referring to my brainless LabVIEW presentation, in which I talk about mindlessly passing mindlessly passing class values through VIs that do not modify those classes. I still strongly believe in that. However, if a VI can modify the error cluster value, the error obviously needs to be a pass-through. And you're exactly right. If I've got a VI that does not modify an error, I will tend to not include the error terminals on that VI. In the example that we've got in the slide here, all of those database VIs can generate errors, so they're all going to pass it through. So let's talk about all the different ways you could break the error chain in your LabVIEW code. The first one is pretty obvious, and that is just not wiring the error output that is part of the error chain. So here we've got a series of DACMX calls, and for whatever reason, whoever wrote this code did not wire the error terminal out from the while loop into the next DACMX VI. This is an issue that, as I mentioned before, can be extremely difficult to debug in a large application with a deep hierarchy. Now, there are some VI analyzer tests that can detect this issue. The unused code test can detect whenever there's a loop terminal that's not wired to anything. So that would detect what we see in the slide here. The error cluster wired test would detect if you didn't wire the error output of one of those DAC VIs. And again, I'll give credit to Stephen Loftus-Mercer for helping me put this presentation together. One of the things I had to concede to him when I put this presentation together was to include a few mentions of automatic error handling. This is the first. It will not be the last. However, it will not be the, there will be some less than positive things to say about automatic error handling later. But it is true that if you don't wire the output, the error output of a sub-VI or a function, and you have automatic error handling turned on, you would be made aware if that function returned an error. All right, this is the most fun one, in my opinion. Zero iteration for loops. They are one of the more insidious ways to break the error chain because this is a pattern that people don't key into as much. The previous slide, very obvious that the error chain is broken. This slide, less obvious that the error chain is broken. So let's look at that for loop. It is iterating not on the end terminal, but on the array that's wired to its border. So there might be a situation where an empty array is wired to the border of that for loop. And in that situation, the for loop will run 0 times. And because of the way this code is written, any upstream errors and the incoming reference will become invalid because this for loop ran 0 times. And the reason for that is that if you have a for loop that runs 0 times, your, I guess, intuition, if you're new to LabVIEW or if you haven't really thought about it too much, might be, oh, well, the value that goes into the for loop, that's going to be what comes out of the for loop. So that reference in, that's what's going to come out. That error in, that's what's going to come out. But that's not how it works. With regular tunnels, like what you see in the slide here, a tunnel output of a 0 iteration for loop is going to return what we call default values. Now, that is not a mistake in the slide. I do have the word default there twice. because default values in LabVIEW are defined as the default for a data type if you never change it. So the default for a string is empty string. The default for a numeric is 0. The default for Boolean is false. The default for an error cluster would be no error, error code 0, source string empty. The default for a reference would be not a reference. So those are the default values. So if we, I guess, let's pretend that this is an example coming from, oh, I don't know, how about a nuclear power plant? So let's say the incoming error to this for loop in this picture is error 235, and the source is the reactor core meltdown, may God have mercy on our souls, BI. So that's the error coming into the for loop. But probably because the reactor core is melting down, the array coming to the for loop is empty. And so that for loop is going to run 0 times. And what's going to end up happening is that for loop is going to output no error, and it's going to output an empty reference. And so your error dialog that pops up is going to be from the TDMS close function telling you that there's an invalid file reference. So, you're sitting at your desk at the nuclear power plant, and your error dialog pops up and it says that, oh, I had an invalid file reference from my TDMS close. But then you look down and you see your fingernails are falling off and your skin's glowing green, and it's too late at that point. If only you had not broken the error chain, maybe you would have lived to tell the tale. So this is a really easy thing to fix. Just change those error tunnels to shift registers. If you use shift registers, that's a way to tell LabVIEW that if the loop runs 0 times, whatever came into the left side is going to come out of the right side. So if we turn the error tunnels into shift registers, if we turn the reference tunnels into shift registers, we will find out much more early that the reactor core meltdown, may God have mercy on our souls, VI, returned an error. And there's also a test in the VI Analyzer toolkit that can detect this exact problem and return a failure for your code. But in terms of takeaways for you guys from watching this presentation, every time you implement a for loop, you must ask yourself 2 questions. The first question is, can this loop run 0 times? Now, sometimes your loop is not going to run 0 times because you've wired a 3 to the in or something like that. But if it is at all possible that your loop can run 0 times, your second question is, will my loop propagate errors and any other pass-throughs appropriately if it does run 0 times? And hopefully you're going to say, oh crap, I have tunnels instead of shift registers. Let me go change those. And that'll be the end of that. But that's the point, is I want you guys every time, and we drop a lot of for loops, you guys. LabVIEW programmers use a lot of for loops. I think it's the second most dropped object after case structure. We use a lot of for loops. So we should be asking ourselves these questions every single time we write code with a for loop. Now, the thing about using a shift register is if any iteration of the for loop returns an error, then that's going to basically stop any future iteration from doing anything, because now there's an error value on the shift register. So what if you want your loop iterations to run independently regardless of error? Well, in that case, you would probably write code that looks more like this. So here, we are allowing our TDMS write function to execute even if one of its executions returns an error. We are building up the errors on the loop border and merging them with the error from before the loop executed. And again, that is because the loop might run 0 times. So we want to make sure to preserve that error that came into the for loop. Now, if your array has 1 million elements, maybe you don't want to build up 1 million error cluster values on the for loop border. So you might add a little bit of logic in there with the shift register to only keep track of the first error that happened, whatever. But yeah, since we want those iterations to run independently, regardless of error, we can't use an error shift register. We might want to use one like separately from the input of the TDMS function if we want to keep track of the first error that happened, if we're concerned about a huge iteration count. And then at the end, we merge that first error with the errors that were generated by the loop. And yeah, so parallel for loops, we don't want to forget about them. So here's a parallel for loop. This one might run 0 times, but check it out. It's got those weird arrow things on the tunnels. What are those? Those are called error registers. So an error register can only be created on a parallel for loop. And what it does is it still allows the for loop to run in parallel, because if you guys have ever used parallel for loops, you know that in general, you can't have shift registers on their borders, like passing data between iterations, because that's not possible to do when the iterations are running in parallel. So instead, you can use an error register, which basically behind the scenes generates code that kind of looks like this, but it looks cleaner. And what that does is that the error register still allows the for loops iterations to run in parallel. It merges the error values at that output tunnel, and whenever you wire error tunnels on a parallel for loop and try to turn them into shift registers, it's always going to turn them into error registers. You can't have an error shift register on a parallel for loop. All right, there's questions about simple error handler and error dialogues grabbing your UI thread. I don't know, I'll look at those later. All right, so another way to break the error chain. Can somebody in the audience tell me what is wrong with the error propagation in this VI? I'm watching the chat with bated breath. Merge errors order. Well, VJ, I know for a fact you've watched this presentation before, so like way to go on remembering the answer. But yes, so over there on the right side, let's look at that merge errors function. Now on the surface, it doesn't look like that's a big deal, but let's, I'm gonna draw a little box here so that we can follow the error input. So the error into this VI, which might have an upstream error that occurred before this VI even executed, that's going to go into this function over here, then this function, then this function, then this function. It's being merged with another error, but that's okay. It's on the top input of that merge errors function. We know that it's going to be first in line. But then when we look at the last merge errors function, that's when we see the problem. We see that the upstream error that came into this VI is being merged second. Now, the way that merge errors works is that if there are multiple errors that come into the function, it will use the highest one, I guess, pixel-wise. It'll use the highest input as the error that it outputs. So in this case, if this sub-VI way up in this corner here generates an error, then that's the one that this VI is going to output, and we're going to lose the one that came into this VI, and you never want to lose upstream errors. So watch out for sloppy merge errors ordering. If we look at this fixed VI, we see that the error stream goes and it's the top input there and it's also the top input there. So no matter what happens, we're not going to lose our upstream error that might have happened before this VI. All right, so to summarize, ways to avoid breaking the error chain. The VI Analyzer Toolkit has a test called Error Cluster Wired that will detect places where you neglected to output an error. The VI Analyzer Toolkit has an unused code test that will detect output tunnels of structures that don't go anywhere. The VI Analyzer has a for loop error handling test that will check for the patterns I described earlier about zero iteration for loops. And Stephen made me put this bullet in the slide that you could possibly enable automatic error handling during development. Which will help you sometimes. It won't find cases like that while loop error output, but it can tend to help you. It does require tooling to enable or disable an entire code base. That was one of the best things in LabVIEW NXG, was that auto error handling was a project-wide feature that you could turn on and off. I would like to see LabVIEW move in that direction, so it's no longer a per VI setting. But real quick, I mentioned the VI Analyzer a lot in this section of the presentation. It is very clear to me, based on some content I saw presented at this summit earlier today, that not everybody knows about the VI Analyzer. So I have a presentation available that introduces you to the VI Analyzer, talks about the tool, talks about the tests, talks about the use cases, talks about the type of issues that it can find. If you've not used the VI Analyzer, you should check out that presentation. All right. So let me talk real quick. Somebody asked in the chat earlier about retaining errors. So there is a feature in LabVIEW where you can take multiple error values and wire them into merge errors. Well, that looks like a normal merge errors function, but it's different. You can see it's got a thick line in the middle. That's because I right-clicked on the merge errors and selected retain all errors. Now, If you've never seen this functionality before, it's pretty interesting because we've got a single error cluster coming out of that function. It's not an array of errors, it's a single error cluster. Yet that error cluster magically contains the error information from all three of the incoming errors. And then if you want, there are ways to, basically pull out all of those individual errors from that error cluster like we've got here. Now, my question, this feature has been in LabVIEW for several releases now. Is anybody actually using this? Because I have not used this anywhere in my code, and I have not seen anybody use this anywhere in their code. Yeah, I'm seeing in the chat, several people are saying that they haven't used it. And I'll be honest, I do a lot of debugging in LabVIEW. I do a lot of looking at errors in LabVIEW, and it almost seems like I'm usually, maybe I'm oversimplifying this, but I'm usually trying to figure out one problem at a time. Like, it's not like I'm getting to the point where I'm like, oh, well, my application's having a problem and I know it has to do with TCP and file IO and DAC-MX. Like, that hasn't happened to me. So I'm curious. It sounds like from the chat, nobody's using this. And to be completely honest, I kind of asked this informally because I know LabVIEW R&D is also wondering if anybody ever uses this. So pretty sure Christina and Eric might be here. There you go, guys. Nobody's using it. So, take that information as you will. Okay, let's move on. Error case structures. I feel like I have had a positive influence on a lot of LabVIEW programmers in the past however many years I've been pontificating about this, because I feel like I see error case structures wrapped around code less and less these days, and I couldn't be more happy because it is almost always a waste of time. We don't need to wrap every single one of our sub-VIs in an error case structure like this. And why is that? Is because, like I talked about earlier, all errors are either generated by built-in functions or by G code that you've written. With rare exception, all the functions are going to skip execution on an incoming error. And with rare exception, a block diagram is going to function the way you would expect it to function with an incoming error, which means all the nodes will skip execution and all the outputs will be default values. If I go back to the previous slide, with an error coming in, we can see that this VI is going to output an empty array of files, an empty array of folders, and whatever error was passed in. This code is going to return an empty array of files, an empty array of folders, and whatever error value was passed in. That case structure on the outside is completely unnecessary in this particular case. Now, I will say there are some rare instances where you do want an error case structure around your code. And you can see those here. If your code is manipulating the error stream in some way, that is probably the only time that I use error case structures. We've got a couple of other very rare cases. Maybe your code needs to output strange values whenever there's an error. Maybe your code's going to execute for a really long time, even if there's an error or not, so you can wrap stuff so it doesn't happen. But in general, I'm writing code like what you see here, where my code is manipulating the error stream. The picture on the left is clearing a specific error. The picture on the right, I guess I cut off a little too much because I can't actually see how it's manipulating the stream. But the point is, when your code is manipulating the error stream, you want to indicate in some way why you've done that. And I almost always do something like what you see on the right. I will put the error case structure, then I will put a label on the case structure describing why I put that case structure there in the first place. All right, so let's talk about functions and their error outputs. There's a lot of functions in LabVIEW. There's a lot of sub-VIs. They have error outputs. Should you wire every single error output on your block diagrams? Well, if you're me, you should not. And my advice is that you don't need to wire all your error outputs for a couple reasons. Here in the upper left corner, we've got a format into string function that will never error out. That function will literally never return an error unless your computer runs out of memory. If it does, you've got bigger problems than your format string not working. So if you know a function can't reasonably error out, you don't need to wire its error output. And then the bottom picture is what happens with me all the time. There's a function that might error out, but I don't really care if it errors out. I'm going to try to delete that temporary file. I don't care if I can't delete that temporary file. Maybe the path went invalid a long time ago. I don't care. I'm going to give it a try. We'll see what happens. Same with closing references. I'm going to try to close a reference, but I don't really care if there's an error when trying to close a reference. So the VI analyzer includes in the error cluster wire test, it's got a list of options of things that you can ignore if you don't care about their error outputs, and things like delete and close reference are in that list. Now, let me just talk about automatic error handling for a second. I'm not a fan of automatic error handling, in case you guys didn't know. I feel like, I mean, I don't need to get into the whole spiel, but I feel like it's a crutch that LabVIEW programmers might lean on too heavily, and instead they should just, propagate errors the way they should be propagated in the first place. Wire the terminals you care about, ignore the ones you don't. I always turn this option off in my tools options when I get a new LabVIEW. Well, technically I copy over my LabVIEW INI file, so I don't have to go in there, but there's the option to turn it on new VIs. I always have that turned off. There's a VI analyzer test that you can run over your entire code base. In an earlier presentation today, Sam Taggart was complaining that VI analyzer tests don't modify or fix your code for you. This is an example of a test that does. So you would point this at your code base and say, please turn off automatic error handling on all the VIs, and it would just do it. Whenever I see code that has a clear errors or an empty flat sequence just dangling off the side of a function, my number one thing is, oh, this person is trying to pacify automatic error handling. And my number two thing is, why is this person trying to pacify automatic error handling? Just turn it off. You shouldn't have to pacify the editor with your code, with your source code. Okay, I'm starting to get into it. I have a presentation where I pontificate about this topic. It's called An End to Brainless LabVIEW Programming. And the link is there in the chat. So some closing thoughts. This is going to be hard, but you really do need to make a conscious decision about every error wire you create or don't create on your block diagram. It's one of those things that, again, just coming back to my brainless LabVIEW programming idea, it's one of those things that can become very brainless in LabVIEW, but it really shouldn't be. You really should be thinking about the ways that you are generating and propagating errors on your block diagram. And when you do that, you should be able to open a block diagram and at a glance, know exactly how that diagram is going to function with an error condition. And hopefully you're going to know that because the code is well documented and you remember some of the patterns that I described in this presentation. In my opinion, if you use automatic error handling, there's no way to know if there's going to be a random pop-up error while you're developing your code and whether you even care about that random pop-up error or not. Your biggest takeaway, other than how to pronounce my last name, is that the error chain should be immediately obvious on every block diagram. That is all I have, everybody. You can download the slides there. Hopefully I'll have this recording up pretty soon. And dnat.org is where all of my presentations live. Any questions or anything? It looks like we've got a few minutes before the next presentation. Thanks for the virtual claps, everybody. There's here. How about if somebody? I don't feel like scrolling up. If somebody had a question that I didn't answer, just copy paste it, and I'll answer it. What is the likelihood of the error cluster ever becoming a class? I don't work in LabVIEW R&D anymore. I have no visibility into whether this is something that's on the roadmap. I have not heard of that being on the roadmap. So Enrique asks in the chat, should the error VI include the error number in the name of the VI? You know what? I thought about this a lot as I was putting these slides together. And I guess I chickened out because I was really leaning towards making that recommendation, but I didn't quite feel, I guess, confident enough to make it because I've never done that. What I always do is I have the -- error VIs, again, the Fabiola way, and especially if Antidoc is going to be able to generate automatic documentation, I didn't want to recommend something I'd never tried before. It's an idea that I think has merit, but, and again, I'm speaking about having the error code number in the name of the VI. I can't think of a time where I changed the error code in one of my error VIs, and I've written a ton of error VIs. So I'm inclined to say maybe it's a good idea because even at that point, it's even easier. You literally do a project find for a number, and then you go start, you don't even have to go reference your spreadsheet or whatever, you dig through the VI diagrams. But since I've never tried it, I didn't quite feel like I should recommend it yet. But it is definitely something I'm going to keep in mind the next time I need to write some error VIs for a new library or application. Yeah, Wes mentions it's another thing you have to edit if your code's ever changed. My codes have never changed. I've written hundreds of dash dash error VIs over the past decade, and I've never changed an error code. Now I say that um, DQMH changed their error codes because when DQMH first came out, they used like 5001, 5002, but then NI gave them an error code range just for DQMH framework, and so they changed their error code. So that would be a case where, yeah, they did change. Enrique points out, what if you have multiple error VIs with the same error code inside? I've never done that because, again, I want to have a single spot where I go to look for a particular error code. But if you did do that, then yeah, the number in the name wouldn't work. Maybe put them in the icon. I've had some ideas about putting more information in the icons of VIs. And yeah, John points out, you don't change the codes. And like, I think DQMH had a good reason. I think the fact that they were gifted an error code range from NI, they should probably use that, right? Now you know, what are they, 403? They start with 403, I think. If you see a 6-digit error code with 403 at the beginning, you know it's a DQMH error code. So again, it's nice to be able to quickly jump onto that. Yeah, you guys put the numbers and the icons of GPower. So yeah, those are good recommendations. Since I haven't done them, I didn't want to recommend them in the presentation. But yeah, thanks for chiming in, everybody. What other questions do y'all have? Yes. So if you always use the 5,000 error codes, there's a decent chance that another API that you're using is going to use the 5,000 error code. I feel a little bad that in the example I gave in my slides for my servo motor driver, I was using the 5,000 error code. I probably should have picked a different one. But yeah, that's a good point. Maybe I should have used -8,000. Nobody ever uses that range, but it's one of the custom error code ranges. It's kind of like, picking a random port for something. Like, you've got 65,000 possibilities for a port, right? Like, what are the odds that somebody else is going to pick this one? See, Aaron uses the -8,000. All right, we'll all use, how about, what were they? 500,000, 509,000. I'll pick that one. The question is, can you apply to NI to get a range of error codes? I don't know what procedure Delacour went through to get their own error code range from NI. So oh, hey, look, wait, Quentin, does your link answer that question? How to get a custom range from NI? I don't know how to do it, but hopefully somebody, oh, darn. Yeah, I don't know how to grab them from NI, but yeah, DQMH got them. Okay, so VJ says custom error codes are not handled properly. I get undefined error. That's because there's an error code database in LabVIEW, and those custom ranges were specifically picked for things that NI does not use in their APIs. So the only way for you to get them to be defined is to create either error code text files or to build error VIs like I talked about before. Like if you're just wiring in a random custom error code, it's always going to be undefined. In fact, I think, well, since the slides are done, I think even the DQMH ones, like if you try to put those in the explain error, I think that even then they won't work because they don't have an error text file. Let me see if that's right. Since I don't remember exactly what they are, that's why I'm opening one up. Yeah, so you have to use an error code text file to get this thing to say something other than this error code is undefined. But the thing is that, let's see, that's probably a private VI. So even though the explain error says it's undefined, this is still going to give you the message that was wired in with the string. So in terms of simple error handler, the error code is undefined, doesn't really matter. All right. Maybe time for like one more question. All right. Well, I think everybody's probably ready to move over to the next presentation. Thanks, you guys, for attending. Thanks for your good questions. And of course, you can send me private messages in this platform if you have any follow-ups that we didn't quite get to in the chat. But yeah, thanks again, everybody.